Dokun Faduyile, going to be talking about the CUDA Image Processing Toolkit. Uh, this is the toolkit for homework CPS5260, homework number 6. This is basically the process of this is to go through the CUDA programming, how to go through imaging processing. We have a homework that was provided to us, and based on the homework, we have a clear objective of what the job, what we really want to do. The objective include a very well clear objective, which is to implement 4 CUDA kernels. We design a modular code. We provide them CLS selector for flexibility. We also look at the performance, which include the benchmark of the GPU versus the CPU performance, and automate the reproducibility with scripts. My goal is to see how I can get all of the different kernels, different selectors of the operation, and I can put them and run them in scripts. So basically, let's just go through the main goal. Like I said, the main goal is to run all of that. So basically, what is the coder? Coder kernel, what is this actually doing? So the main program basically handle the CLI passing. It take memory allocation and the kernel launches. So on the CPU side, I use malloc, right? Malloc is the one that gets information from the CPU, and then on the GPU side, which is the graphic processing unit, I use the CUDA malloc. So basically, get some information from the host, right? Get information, which is what I want to do, the width, the height of the size of the image I'm going to make. I get the memory, which is the memory allocation using malloc, which is on the CPU, and then on the GPU, which is the same thing for me to see what are the different kernels and that will be improvised. So this is just a major workflow of how I have the system going from the coder and then to the GPU. All right, so now what is the parameter of the stuff that we want to do? So basically we have a command line parameters. Basically for the toolkit that I'm trying to work on, for example, I have operation that is going to blur an existing image, input image that is given to us, and I select the block kernel, which is going to take certain dimension. It will take the image, the width, the height, and the weight, and then it look at the existing image and blur it out. So basically this is just what kind of parameters, how I'm going to call out that operation for it to be able to do uh, that action. Look at look at the grid and be able to send out a block and update the image. So the image will give me, I will pass the weight, the height, as well as the threshold of the image. And then when I call my subroutine for the blur, it'll be able to make all the changes and take all the iteration control and the number of passes that is going to go through it. So um, and here the kernel, how do I launch? This is just an example of the kernel with grid and block dimension. The block kernel computes weighted averages, edges detection, calculate the gradient, sign generation, produce the wave path, and the vignette applies racial attenuation. So basically what the kernel is doing is it look at the operation that has been passed, take it, weighted it, compare it with the input ppm, and start the process. Basically, the process I'm going to do, I'm going to do a blurring, I'm going to do an edge, I'm going to do a sine wave, and I'm going to do a vignette. So it's going to take all of those 4 operations and process it. So this is just an example of how it take, just have a global declaration of a block kernel, right? It take the image, press a floating into it. It take all the weight, the height, and the weight as an integer. So you look at it, you compare that, you look at the dimension, you look at the thread, how it's being formatted, and then you compare, you do the weighted average of the neighbors. So that is for blurring. So this is just a typical example of how the blurring is going to look like, and it's similar to what the sine wave, the edges, and also the vinaigrette is going to be. So after putting all of these individual codes together for each of the different operations, what I did is I created a script that allow me to be able to run all of the different operations that I want to do. So basically I created, going with a C++, I use C++ based on the uh, ppm CUDA program that's the professor provided as an input that created the input ppm. So I just this is the compiler that I use. So it's just an example of the compiler. Here we have a iCompute 89 code. So this is just talking about the actual. It's talking about the actual GPU type that I use. So for example, on the one that for the one that we use, so it was able to get information, look at the inputs ppm, which is the ppm that was created. Sorry, the ppm that was created, and then take that image and blur the image, and then it outputs a blur ppm for that one to do. So basically, this script create a batch script that runs all the four operations sequentially, and then log the timing, because I want to look at the operation, the performance of each. And then the other thing I did, I did a batch script. I also wrote a Python plot. Basically, what the Python is doing is just to take the information and be able to plot, uh, you know, the performance. How long does it take for each of those to be able to compute. So that's, I use Matplotlib, which is Python programming, to be able to help me compare the GPU, the CPU performance evaluation, compare it to the time and also to the operation. And I look at each of the different operations that I was going to use, which is the blur, the edge, the sine wave, and the vignette. So, and then I plotted it. I look at the benchmark comparison, and I'll show you the result of that. So, like I said before, this Arc Compute 89 was a code I was able to use for the particular type of GPU that I was using, which is the RTS 4050. Uh, so now, going through the operation, able to wrote a code that actually measure the timing of each of these operations. So for the operation, I know the GPU time in microseconds. I know exactly how long it took for the blur operation to perform its action, as well as the edge detection, and then likewise, the sign generation. So basically, what this is doing is just compare uh, the GPU time, the execution time, and achieve, what I achieve between about 12 and 13 times faster for each of them. So that is the essence of this, for me to be able to see their performance operation. So now, what after doing that, I look at the actual CPU. Like I said, I pass memory through the malloc, and then the GPU I use uh, through malloc for GPU to get memory into it and be able to pass the information. So when I look at the performance operation, I could see that, for blurring, the CPU is actually about 150 microseconds, but the GPU is almost about 12.5. So it's a little bit slower on the GPU, and likewise the edge. So these are the direct timing that I was able to get from that. And you can see the speed up is almost about 12 times, 12 to 13 times faster between the CPU and the GPU comparison. Okay, so from there, I was able to look at, our goal is, one of the goal is to get the actual input ppm that was created and compare side by side with the output of the operation, like for blurring, for edging, for the sine wave, and also for vinaigrette. So after looking at their performance, I actually look at the actual uh, input that was created, and I compare all of them together. Let me share this. Let me share this with you right quick. What we, one second, yeah, sorry, I need to share one. Is it? Uh, Sorry, I have it open, but it's not here. So, basically, from the report, I have each of those, how each of those have been compared to each other. So let me switch the screen for you. All right. So on this report, as you can see, so my goal is to look at, this is the original input image that was created. And then I compare it to the blur image, which is the actual blur image. As you can see, it's a little bit darker, it's a little bit blurred compared to how the input image is. Same thing, I compare the input image and see how that is compared to the edge output. So basically it's take the image highlighting edges and contour based on illumination and gradient, and of course when you do the edge detection it turns into pretty much dark. And the sine function generation, basically you just take what you have and try to create a sinusoidal wave. And as you can see clearly, I look at the input and just take the whole inputs, make it more like a sinusoidal. You can see, if you actually put in a curve, you see how this one has looked like more of a sinusoidal wave. And of course the vinaigrette, this is just look at the image with radial darkening towards the corner, which is emphasizing the center. So as you can see, this center here wants to preserve the center, while it puts some darkening at the edges of it. So basically, this is just how those information were compared together, from the original image as it compared to the image that was created based on the code. All right. So now, what are the things that we find? What are the things that was challenging in going through this program? One of the major things is when I was running this program, actually I ran it on my own personal computer. I did not use the same sender because I did not have access to it. One of the things I found out is when I was finished the program and trying to run it, I keep getting an error, which is give me a null. That's I have, especially in the sine wave, I have uh, an error that is known. And what I find out is that the my GPU, the the revision of the software that was there was 12.7, which causes a PTS error. So in doing that, what I just did is just go back and update it. It took me a while before I could realize that, and after I updated it, I was able to resolve it. And that is one of the reasons why I use the compiler and pass this code, which is the compute 89 or code SM89. I don't really need to use both, but using both is doesn't really make a difference. So code SM89 is enough for you to actually pass to look at the GPU and get the actual information from the GPU. So that was the major challenge that I encountered, and I was able to fix that. So based on this, there are some things, just sorry. So based on this, one thing I found out about working on this thing is what are the ways that this thing can work? What are the things I can use it to do? Just something that we can look as part of future, as part of more research work that we can do in future is, I can plan to extend the toolkit with more filters. I can add CPU fallback, automate benchmarking across. I can do it across resolution and package it as a reusable library. So that means that somebody that wants to use it in the future can just call a subroutine and use it. So those are some of the future work that this particular CUDA imaging processing that we can use it, that we can do additional research on. So that is about it. In conclusion, the modular coder program, the toolkit demonstrated modular GPU programming with reproducible workflow. Basically, I was able to look at the different selectors, the different operation that I want to perform, compare with an existing image, process that image, and then give me an output of the image, and be able to see and compare that with the performance of each of the process. How do they, what kind of information I'm getting from the CPU as well as the GPU. So the GPU acceleration provided substantial step speed up over the CPU implementation, as already seen, and that is the essence of having a good GPU on your system. And CUDA actually allow you to be able to process and do a lot of more processing. So overall, um, I think this provide a very clear workflow and empirical benchmarks. Just in this particular homework number 6 have allowed me to go through, the type of snippet of the code that we use, and then the overall how the performance of the CPU as against to the GPU, and the performance of each of the accelerate of the operation that was selected, and how they compare to each other with a random input ppm that was created. How do they compare with, when you process those with it? I was able to use scripts and Python to take some of those ppm that were created, change the image, create, use image mark to take the ppm and convert it to JPG, and from there was able to use it. My programming, I use latest, and put all of those in the latest for you to be able to have a good latest report. So that is the conclusion of the program, and how the program was able to, at the end of the day, it was uh, it did what it's supposed to do, and able to see the clear, when you do comparison between the inputs um, ppm compared to the process, after you've done your operation, clearly shows uh, the program, and the effectiveness and efficiency, and how powerful CUDA could be in processing imaging. Okay, thank you. Have a good one.